Welcome back to Science Quickly. I'm Rachel, and today we are at Brookhaven National Laboratory at the country's only particle collider. And I'm here with scientist Alex Jentsch. Nice to meet you, Alex.
Nice to meet you too, Rachel.
So, where are we? What goes on here?
Well, right now we are in the experimental hall for the STAR experiment, which is one of the two operating experiments right now at the collider. Mm-hmm. And this monstrosity behind us is basically just a very large digital camera that we use to take pictures of collisions of particles.
Wow. And what's the point of taking a picture of a collision of a particle?
Well, the only way that we can really understand what's going on inside of the atom or inside the nucleus of the atom really is by destroying it. And so basically you can imagine this digital camera taking a picture of a firecracker after it blew up and then trying to put it all back together. So it's basically the only tool we have to look inside the nucleus.
And what kind of stuff can we learn with that?
Well, there's various different things. So the original reason that we built this facility, built this collider, was to study the early universe. So we were actually trying to recreate stuff that would have existed right after the Big Bang. So we obviously can't go visit the Big Bang very easily unless you're a Time Lord. And so ultimately, the only way we can do this is by trying to recreate those conditions in the lab. So that was kind of the first main pillar of the science program, was looking at a situation where protons and neutrons were not protons and neutrons. They were actually melted into their constituents for a very short period of time. So we do that for very, very, very small amounts of time in collisions in the middle of this detector. Alternatively, we can also look at just basic structure of the proton. We can understand things like its mass, its charge, and its spin, which is kind of an esoteric aspect of a proton. But that's another thing we can do with this camera.
Cool. It would be great if you could just give us a quick overview of sort of the basic terms we need to understand to wrap our heads around this.
So atoms are already fairly complicated. So we learn in chemistry that atoms have these electrons zipping around the outside in this cloud. And then if you go deeper into the inside of the atom, you get to the core thing that we call the nucleus. So the nucleus is made up of these positively charged particles called protons and these neutral particles called neutrons. And for a long time, we thought the electrons, the protons, and neutrons, they're fundamental. Well, then we looked deeper. We got new tools that we could use to probe deeper inside and found, oh, there's stuff inside the proton and neutron. Dang it, that's more complicated now. So we found these objects. We had no name for them yet. We didn't really expect them to be there. And one of the first things we had to figure out was what they're doing, what their properties are, how they're held together. They seem to be always bound up inside the protons and neutrons. So we started calling these things quarks because we couldn't really figure out a name. We found something in a James Joyce novel that sounded like it matched the weird thing we found. And they're seemingly glued together inside the protons and neutrons. And we know that from the electromagnetic force that photons are kind of the force-carrying particle between charged items. So electrons, protons, they see their electric force by being able to exchange a photon. There must be something similar for quarks. And so since they're kind of glued together, we thought, okay, maybe this particle's called a gluon. Maybe it's the thing that's actually communicating this much stronger force than what we see for electromagnetism. And so from all of that, we learned that the strong force is actually much stronger than electromagnetism. It's communicated via this thing we call the gluon. And so all of a sudden, a whole new branch of physics became a thing and is now why we build these new machines.
Quick follow-up, what's the strong force?
So the strong nuclear force is actually what binds protons and neutrons together and eventually binds them inside of atoms together. Because if you think about it, protons have positive charge, neutrons have no charge. How are the positive charge items holding themselves together into a nucleus? So the strong force allows the nucleus to actually hold together.
So can you walk me through what goes on when the accelerator is turned on? You know, what does an experiment entail?
So the accelerator part is immensely complicated. It's actually a whole complex of accelerators. So you can picture it kind of like the entrance ramp onto a highway. So we start the cars off, after a red light on the access road, they eventually get on the ramp and then they get on the highway and speed up.
Right.
That's kind of how the RHIC facility operates. RHIC is short for Relativistic Heavy Ion Collider. RHIC is easier to say. So RHIC is kind of like the highway, and then the other parts of the complex are like the access roads. That part is a whole set of expertise and a whole lot of challenges, and getting the particles into RHIC is only half the battle. Once they're there, they have to accelerate. So we have to basically accelerate them at the same time that we ramp up all of the over 1,000 magnets that are inside the ring.
Wow.
So those ring magnets are being ramped up in their field at the same time that we're speeding the particles up really, really close to the speed of light. And then eventually, our friends at the collider department use other magnets to force the two beams to collide at the center of our detector, and then we start working. So we're in a control room on the other side of this building. We turn on all of our detectors and start taking data. And that process goes on for about 8 hours at a time. And so while we're in the control room, we babysit all of the detectors, make sure the data taking is going smoothly, and things always happen that we don't expect. And so we try not to run in the middle of summer, for example, because it gets hot and the power grid on Long Island is not so happy with how much power we're drawing. And so eventually we get little dips and that can shut things down for quite a while. So just getting the particles to the middle of the detector is really, really, really hard.
So what are some examples of findings that have taken place because of the work here at Brookhaven?
So one of the initial things that was really interesting is that when we smashed these particles together, we originally started smashing gold ions together, and there was a reason for that. To recreate the early universe, we want a lot of density and a lot of temperature. And so by smashing heavy ions together, the hope would be that in a very, very, very tiny nuclear scale, you recreate the early universe. Really, really, really small. And the thought was that when we do that, the energy density becomes so high that the protons and neutrons melt. And you get what originally we thought was a gas of the quarks and gluons inside. That wasn't really what we ended up finding. We actually found that they don't really behave like a gas at all. They kind of behave like a liquid, which is really not something we expected. And so as we started to do more work and study different things about the properties of this quark gluon plasma we create inside, a lot of it was not what we really expected it to be. So for example, we expected, because it might be a gas, that it would be fairly weakly interacting, which is not what you'd expect from the strong force, right? But it turns out it's actually quite strongly interacting. That's why it moves kind of like a fluid. All the particles actually kind of talk to each other. And that has consequences for some of the things we try to measure. And so many of the things we initially measured were quite different from what we expected. As particles go through this plasma, they lose energy. And so when we measure them in our detector, they are not really behaving the way we originally thought they might. The other aspect of things that we try to study here is the basic fundamental property of the proton, the spin. And a long time ago, we found out that the proton spin is not just coming from the quarks. It's coming from some combination of the quarks and the gluons. And so we actually made some of the first constraint measurements here at STAR and at Phoenix down the road that showed the amount of spin that could be coming from the gluons. And that was like a first ever measurement. So now the goal is to figure out the last part, which is how the motion of the quarks and gluons contribute to the proton spin. So we can't answer all the questions with one facility. And so the hope would be that we can use the new facility, the Electron-Ion Collider, to start looking at that as well.
Yeah. Well, and speaking of, answering new questions, one of the reasons we're here is that this is sort of the end of the line for this version of the accelerator, as far as I understand it. Can you tell us a little bit about the transition that's happening?
Yeah, so at the end of this year, we'll have our final data taking for RHIC. And at that point, we spend a couple of years taking all this stuff out because we have to make room for the new facility. And that process is really difficult because you can see this is not a small piece of equipment. In parallel, we'll also be retrofitting whole sections of the accelerator to build the components for the Electron-Ion Collider. So it's exciting. We're really ready for the new physics, but it's also bittersweet because a lot of us have been working on this for a long time. I've been working on STAR for like 13 years. And so I have fond memories of sitting in the control room with friends from all over the world, eating, really salty snacks to stay awake and drinking coffee. And that's going to be, going away at the end of this year. We'll have quite a long time before we start taking data with the new facility.
Yeah. And what's the reason for the changeover?
So the kinds of collisions we do right now are either gold smashing on gold, or proton smashing on proton, or even proton smashing on gold. The problem there is that you have two items that are full of quarks. They're really complicated items. And as you speed them up to really high energy, they get more complicated. And smashing two really complicated objects together means that trying to study it is not easy.
Yeah.
By using electrons as one of the beams instead of another proton or an ion, so you have an electron smashing into an ion, the electron basically serves as a source of light. It serves as a source of photons. And so you can actually take essentially snapshots of the nuclei of the protons. It's a cleaner collision environment. You can't study everything that we study here. You can't study a quark-gluon plasma, for instance, because you don't have the energy density of all those quarks together. But you can study what the nucleus really looks like at a very, very, very small scale. You can study what the nucleus might look like before it would have collided in RHIC. And so in some sense, you can actually use the data we'll take 10 years from now to reanalyze data from now to try to understand more than we do now, which means we have to preserve all the data that we've been taking for the last 25 years. And so there's a whole discussion now about the computing facility resources we're going to need to store all of the data we've been taking, make sure it stays safe.
Can you give me a sense of how much data has been collected in that time?
Right now, we're collecting an average of something like 15 petabytes per year.
I don't even know what a petabyte is.
So a petabyte is see, we're at terabytes, gigabytes, so it's a million gigabytes.
Wow.
And we're doing that now per year. It's gone up with each passing year. So when we first started taking data, we were not taking so much data. The machine was at a much lower rate of collisions because we had to make sure the detector was safe. And computing power was not as good 25 years ago as it is now. So basically, as computing has caught up with what we want to be able to do, we've increased the amount of data we take with each passing year to kind of make use of all the computers we have available now.
Yeah.
And so we've really stretched them to their max.
So, as viewers may have noticed, we have changed locations.
Magically.
Yeah. So tell us what goes on here.
Okay, so earlier we saw the detector. That's a digital camera that takes pictures of everything, but the everything we want to look at has to come from somewhere. And this is one section of the accelerator that actually brings the particles down to star for us to do collisions and then take pictures of them. So there are a little over 1,700 of these individual magnets all the way around the 2.4 mile circumference of RHIC. So this tunnel just goes on and on all the way around, and we have a road on the outside we can use to actually run around it. And ultimately, this whole section here is really just focused on maintaining the particles in the ring. Inside, we are using liquid helium to keep these things at superconducting temperature. When I say superconducting, you might ask, what does superconducting mean? Well, normal metals, when you try to put electrical current through them, they're going to resist the flow of that electrical current. And the act of resisting that electrical current causes them to get really hot. The amount of current that we need to actually get the field that we want is in the thousands of amperes, which is a lot. A fraction of an ampere can stop your heart. So imagine what thousands can do. So the amount of heat you generate with a normal conductor would not be good. You basically melt the wires after a while. So by cooling them to temperatures that are far below what we normally experience, to 4 Kelvin, which is 4 Kelvin above absolute zero, the metal that we use is able to be superconducting at that temperature, meaning that it essentially has no resistance to current flow. So you can pump massive amounts of current in without generating a lot of heat. So each of these tubes contains the pipe for the particle beams to actually go through, and then we have all the cooling that actually is used to maintain the magnet's temperature, power cables. So ultimately, we just have this times about 1,700 around all of RHIC.
Wow. Why does it have to be so long?
Well, one of the difficult things is getting a high enough beam energy to do the collisions we want to do. And because of the challenges of actually accelerating particles, as you accelerate them faster and faster, their radius wants to get larger in the beam. So what you have to do is have magnets that are strong enough to maintain them at a fixed radius around the ring as they accelerate. And so I said earlier when we were talking about putting particles into the machine, that as we accelerate them in speed, the magnets have to be slowly ramped up at the same time. So the size of the actual ring plus the magnetic field strength kind of dictates the maximum energy you can have. And so we kind of push these magnets to their absolute limit to get the beam energies that we get.
It is pretty cold in here, so why don't we head back to STAR to chat a little bit more about what's going on.
Sounds good.
What kinds of questions are you most excited to try to answer with the EIC?
So for me, I'm probably interested in the stuff that's the less sexy aspects of the physics. I really want to know the basic fundamental aspects of the proton that we don't know. The proton mass, for example, it's a given. If you go into a chemistry textbook, there's a mass number there for the proton. But the quarks don't make up most of that mass. 1% of the mass of the proton comes from the quarks. The rest of it is coming from the strong force itself, these interactions inside the proton. We still don't really understand how that works. And that's basic.
Yeah.
We know how much things weigh. We measure this all the time. Why don't we know how a proton gets the mass it has?
Yeah.
So that's interesting to me. But then also even the proton spin. Spin is a less understood quantity. It's more esoteric, but we thought originally that this was coming just from the quarks. And we learned that only about 30% comes from the quarks. So where the hell is the rest of it coming from? And so the EIC gives us the ability to combine data that we take at RHIC with the new data from the EIC and hopefully answer some of those questions. There's stuff that's more interesting to other people in the community, such as what happens when you take a nucleus of gold, for example, and you accelerate it near the speed of light, and now it's incredibly complicated. It's quarks, it's gluons, but it's many, many, many gluons. The question is, does it just keep producing gluons infinitely? Or at some point, does that production cease? If it does the former, that's new physics. That's going outside of what we know from quantum mechanics. If it kind of saturates at some point, then that would be something we more or less would expect, but we don't know. And that's kind of studying something that's in the same ballpark as the quark-gluon plasma. It's basically a state of matter that is dominated by the strong force. To people who have been interested in the RHIC program, this is probably the fundamental thing they want to focus on, is the heavy ion part of it, the really crazy stuff that happens when you make a heavy ion go near the speed of light.
Yeah. And also, very obvious question I sort of started with, how big is it?
So this thing is a little bit bigger than a 3-story house.
Wow.
It weighs about 1,200 tons. The detector that will replace this for the EIC weighs a few hundred tons more. It's not small. And most of what you see that's heavy is iron. So there's a big magnet inside of this, and that magnet has to have a place for those magnetic fields to go. So we have iron to protect, remove all that magnetic field. And then we have lots of detectors. Somewhere like 10 subdetectors inside, but they're made up of thousands of components.
Speaking personally, it's really hard to wrap my head around like what all these different components do. Do you think you could show us around a little bit?
Yeah, sure, of course.
Awesome.
Okay, so this is STAR, which stands for Solenoidal Tracker at RHIC. Once again, big name, small word, much easier. So that tube that you see up there is the main beam pipe where one of the particle beams comes in. There's the same one on the other side. So behind this wall is a set of magnets that are coming out from the main part of RHIC. Particles come in, they collide in the middle. But even before we actually start doing anything fancy with the inside part of the detector, we have to figure out how we actually can make measurements. Mm-hmm. And so we want to measure things like the proton or any particle coming out of the collision. We want to measure its velocity, its momentum. Since it has a charge, we can exploit the fact that it's electrically charged by immersing the entire detector in a magnetic field. So all this blue stuff that's sitting around here is iron that's part of the magnet system. What's good about that is as the particles come out, if they have an electric charge, they're going to follow a curved path in the magnetic field. Mm-hmm. That allows us to figure out what charge they have depending on which way they curve. And then we can use the radius that they make. If you draw a circle that covers the whole entire thing, what momentum they have. So the magnet is really important. And it's majority of the weight we have for the detector is coming from all the iron for the magnet. So after the collision takes place, the digital camera is not really one camera. You can imagine it like being 15 different kinds of cameras from different brands with different levels of resolution, all taking the same basic picture, and you have to combine everything together at the end to get one full picture in 3D. So the inside part of the detector is basically just an empty volume of gas. It's a mixture of argon and methane. The charged particles go through, and as they go through, they leave a trail behind. And we have detectors on the outside of this volume of gas that can see those trails. And then as you go out of the onion into the outer layers, we have detectors that measure how fast the particle is going, so we can get the velocity. And we also have detectors on the very outside that are called calorimeters, which actually are not from particle physics, they're actually from chemistry. Yeah. You use them to figure out how much energy is inside a piece of food, for example.
Sure, yeah.
And so we can basically combine information from different detectors to get a full 3D picture of everything. And that's really hard. And we do that thousands of times per second, and then have to analyze all of it after the fact. So we'll move on through this perfectly clear environment to walk. And you can obviously see that there are many cables here.
Yeah.
Now we have combinations of cables that supply power, cables that pull information off, so you have Ethernet cables, and then these little orange cables that you see here, these little pairs of orange cables, those are fiber optic cables, all existing together and all can break at some point.
Yeah, I was going to ask, what happens when one of these many cables breaks?
When one of these cables fails, it becomes an effort to try and figure out which one it is and then replace it. Wow. We don't actually take the old cable out, it's buried, so we just add a new one on top. So after 20 years, you can imagine that the crow's nest here becomes increasingly insane.
Wow. Can we go up the stairs?
Absolutely, just make sure you hold the handrails.
Okay. Why don't you go first?
Okay, cool. So we're kind of at the underside of the STAR experiment right now. And actually, if you look in this area where the railing is, there's already detectors on the outside of the onion. So if we can put a detector somewhere, we're going to. That's kind of our motto. So these detectors are used for measuring particles called muons, which are basically really heavy electrons, and they don't live very long. They decay after a few microseconds. And so these detectors were installed kind of in the 2012, 2013 area, and they actually surround all of STAR. And so basically, the question is, do we have space for something? Yes, put a detector there. Because there's probably something that we can measure that we don't have the ability to measure right now. And so we ultimately start running out of space only because the building is only so tall.
Sure.
So this is now the second floor of STAR. And you see kind of the same basic thing. You have lots of computers and racks that are used to take the initial data. But now you have a little bit of a better view of the outside of STAR. And you can see these things that are sitting on top of these muon detectors I talked about, but they're actually mounted on top of another detector. And so in these boxes just below that, we have this calorimeter detector that I mentioned earlier that's used to actually measure the energy, or at least the power supplies for the calorimeter. So that's the other part of this that's really important, is that we have detectors, yes, but those detectors have to have power, they have to have cooling, they have to be able to pull data off, And that's the part we always kind of forget about. You can't just put something there and hope it takes measurements. You have to power it. So ultimately, this is one of the things now as we move toward the EIC that we're taking into account, because we want to have a more complicated detector that can do different kinds of measurements, and we have to take into account where all the cables go. And so when we do simulations, we don't just simulate the detector, we actually simulate all the cables as well, because it's material. Particles go through that material and they might lose energy.
Yeah.
They might create a new source of more particles, and that could be good or bad depending on what you want to do. Now if we go up to the top, we can actually see a huge view of the whole interaction region. This is what we call this area, and get an idea of how tall the detector actually is.
Awesome.
All right, we're at the highest point STAR can maintain, so please make sure you hold the handrails. In a normal year nowadays, we easily collect several billion collisions in a given year. And that's gone up from what we had early on. We've drastically ramped up the rate at which collisions take place and the capability of the detector to record them. You hear me saying things like billions and thousands and millions. This is the scale we're generally talking about to study something so small. We need a lot of data to be able to actually study some of these things with enough precision.
When you're like talking to a member of the public and physics makes their head spin, what is your headline, like, this is why what we're doing is really cool and important for them?
Well, we're made of protons and neutrons. Everything around us is made of protons, neutrons, electrons. They're fundamental. And we have an understanding of quite a bit of it. I mean, our chemistry textbooks and physics textbooks, there's a lot of information there. Mm-hmm. But isn't it interesting to want to understand how these things achieve their basic properties? We know they have an electric charge. We know they have a mass. At the end of the day, it's a basic thing for human nature to try to understand the world around us. If we know we're made up of these things, we don't understand those things, it should be something that just drives our curiosity. Additionally, it's really cool to be able to study things from the early universe in a laboratory environment. And the fact that you have to build something this large to study something so small is also rather insane.
Yeah.
So in and of itself, this is just kind of a wild idea that we have a machine this large to study something that we cannot see with the human eye.
Yeah.
And so my hope would be that that is enough to drive someone toward a little bit of curiosity. You know, what are we made of? Why are we made of it? How does it have the properties it has? That's really what kind of drives me toward it.
Yeah, I think most people would agree that understanding the basic particles that make up literally everything is pretty important. So thanks so much for taking the time to tell us about it and show us around.
Yeah, thanks for having me, and I hope to see you again in 10 years when we start taking data with the EIC.